On the 20th of March 2023, the Intergovernmental Panel on Climate Change released their latest report, which held humanity responsible for almost all global warming over the last 200 years.
The rate of temperature rise in the last half century is the highest in 2,000 years. Concentrations of carbon dioxide are at their highest in at least 2 million years. The climate time bomb is ticking.
If we are to solve the climate crisis, the world needs to reduce 45% of its collective greenhouse gas emissions by 2030 and achieve net zero emissions by 2050. We are now here, so we are already behind schedule. But while our task is harder now, it is not impossible. The Intergovernmental Panel on Climate Change has modelled several different ways that we can still achieve our net zero goal. The common factor for nearly all of them is that we need to remove a lot of greenhouse gases from our atmosphere as well as reduce our current emissions. One reason for this is to compensate for very expensive or hard-to-abate emissions. These are greenhouse gas emissions that are currently difficult to reduce due to technological limitations or a lack of viable alternatives, such as CO2 from aviation or methane from rice fields. Another reason is that we have to deal with the excess emissions that we have already released into the atmosphere. And the longer we wait with climate action, the more emissions we need to remove. That's why, in recent years, there has been a growing focus on carbon dioxide removal, or CDR, as a key technology in our efforts to combat climate change. CDR is when greenhouse gases are physically taken out of our atmosphere. This can be done in many different ways, with the simplest one being planting a tree. A wide range of CDR technologies have been proposed, yet not all of them ensure that this captured CO2 is actually removed permanently.
Once you have taken, for example, CO2 out of the air, you can do two things. You can either use it to make products like chemicals, and that's a way of, for example, replacing fossil fuel and have chemicals which are net zero compatible. But also the important part, as I was mentioning earlier, is the negative emissions. And to do that, it's not only about taking out the CO2, but it's also about preventing it to get back in the atmosphere.
If we want CDR to be a climate-positive technology, we need to trap the CO2 and keep it locked away for what is intended to be permanent storage. When we do this, we end up with something called negative emissions.
So the NCSC+ project, which stands for the Norwegian Continental Shelf, a driver for climate-positive Norway and Europe, is a project where we are actually looking at delivering negative emissions.
This is Simone, research scientist at SINTEF and leader of the NCSC+ research project.
This is a project which is financed by the Research Council through the Green Platform program, and where we explore different ways of achieving that target and how to deploy these technologies. In the NCSC+ project, we are looking at 4 pathways of delivering negative emission, which are bioenergy production with CCS, bio-CCS, direct air capture of CO2 and methane, as well as direct ocean capture, DOC. In the bio-CCS pathway, the principle is that we use the capability of plants to harvest CO2 from the air using photosynthesis, to then use that biomass to then produce energy. And that production of energy, which can be hydrogen, heat or power, then come with the co-production of CO2, which then need to be captured, transported and permanently stored. In the DAC pathways, the principle is to avoid passing by the photosynthesis and basically using an engineered approach of getting, for example, the CO2 out of the air. So that can be done using solids or liquids, sorbent or solvents, that are then capturing that CO2 and then allow us to concentrate it afterward and then send to permanent storage. When we discuss about direct air capture, you hear a lot about CO2 removal, but there's also greenhouse gas that can be removed in this way. This is the case, for example, of methane, which is responsible for 30% of the global warming effect. And while we can reduce this emission in the coming decades, we will still have a significant level of this because, for example, rice production and farming result in significant methane emission that will likely remain even after 2050. So removing this also unavoidable emission to air is also an important aspect of achieving the net zero target. Direct ocean capture, or DOC, is a similar concept as direct air capture, except that here we look at removing CO2 out of water and use the principle that the air and the ocean are in equilibrium, so that removing CO2 out of the ocean also will then make that CO2 present in the air is then moving down into the ocean. An important aspect of negative emission is ensuring that the greenhouse gas which is being taken out of the air is permanently removed out of this. And the reason why we choose these 4 pathways in the project is that all of them can connect to geological storage of CO2, which then ensure that the CO2 will be there permanently. So in the negative emission space, a key challenge now is that with the strong interest and the strong need for these technologies, there are thousands of concepts that have appeared. And the key issue is trying to understand how they can scale, what are the costs also, and what that means. So in this project also, we are looking at what are the challenges to evaluate these and trying also to provide recommendation on how we can better understand the performances of this, because identifying the one that can play a key role is actually a key challenge right now.
We have never been better equipped to solve the climate challenge, but we must move into warp speed climate action now. We don't have a moment to lose. Thank you.